An oxide is a chemical compound that contains at least one oxygen atom and one other element in its chemical formula. Metal oxides typically contain an anion of oxygen in the oxidation state of A2. Most of the Earth's crust consists of solid oxides, the result of elements being oxidized by the oxygen in air or in water. Hydrocarbon combustion affords the two principal carbon oxides, carbon monoxide and carbon dioxide. Even materials considered pure elements often develop an oxide coating. For example, aluminium foil develops a thin skin of Al2O3 that protects the foil from further corrosion. Different oxides of the same element are distinguished by Roman numerals denoting their oxidation number, for example iron, 2, oxide versus iron, 3, oxide. Formation. Due to its electronegativity, oxygen forms stable chemical bonds with almost all elements to give the corresponding oxides. Noble metals are prized because they resist direct chemical combination with oxygen, and substances like gold, 3, oxide must be generated by indirect routes. Two independent pathways for corrosion of elements are hydrolysis and oxidation by oxygen. The combination of water and oxygen is even more corrosive. Virtually all elements burn in an atmosphere of oxygen, or an oxygen-rich environment. In the presence of water and oxygen, some elements sodium react rapidly, even dangerously, to give the hydroxides. In part for this reason, alkali and alkaline earth metals are not found in nature in their metallic, that is, native, form. Cesium is so reactive with oxygen that it is used as a getter in vacuum tubes, and solutions of potassium and sodium, so-called NaK, are used to deoxygenate and dehydrate some organic solvents. The surface of most metals consists of oxides and hydroxides in the presence of air. A well-known example is aluminium foil, which is coated with a thin film of aluminium oxide that passivates the metal, slowing further corrosion. The aluminium oxide layer can be built to greater thickness by the process of electrolytic anodizing. Though solid magnesium and aluminium react slowly with oxygen at STPA they, like most metals, burn in air, generating very high temperatures. Finely grained powders of most metals can be dangerously explosive in air. Consequently, they are often used in solid fuel rockets. In dry oxygen, iron readily forms iron, 2, oxide, but the formation of the hydrated ferric oxides, Fe2O3AX, OH, 2X, that mainly comprise rust, typically requires oxygen and water. Free oxygen production by photosynthetic bacteria some 3.5 billion years ago precipitated iron out of solution in the oceans as Fe2O3 and the economically important iron or hematite. Structure. Oxides of most metals adopt polymeric structures with MOM crosslinks. Because these crosslinks are strong, the solids tend to be insoluble in solvents, though they are attacked by acids and bases. The formulas are often deceptively simple. Many are non-stoichiometric compounds. In these oxides, the coordination number of the oxide ligand is 2 for most electronegative elements and 3 6 for most metals. Molecular oxides. Although most metal oxides are polymeric, some oxides are molecules. The most famous molecular oxides are carbon dioxide and carbon monoxide. Phosphorus pentoxide is a more complex molecular oxide with a deceptive name, the formula being P4O10. Some polymeric oxides when heated depolymerize to give molecules, examples being selenium dioxide and sulfur trioxide. Tetroxides are rare, and there are only 5 known examples: ruthenium tetroxide, osmium tetroxide, hassium tetroxide, iridium tetroxide, and xenon tetroxide. Many oxyanions are known, such as polyphosphates and polyoxymetallates. Oxidations are rarer, an example being nitrosonium. Of course, many compounds are known with both oxides and other groups. In organic chemistry, these include ketones and many related carbonyl compounds. For the transition metals, many oxo-complexes are known as well as oxholides. Reactivity: oxides can be attacked by acids and bases. Those attacked only by acids are basic oxides. Those attacked only by bases are acidic oxides. Oxides that react with both acids and bases are amphoteric. Metals tend to form basic oxides, nonmetals tend to form acidic oxides, and amphoteric oxides are formed by elements near the boundary between metals and nonmetals. This reactivity is the basis of many practical processes such as the extraction of some metals from their ores in the process called hydrometallurgy. Reduction. Metals are won from their oxides by chemical reduction. A common and cheap reducing agent is carbon in the form of coke. The most prominent example is that of iron ore smelting. Many reactions are involved, but the simplified equation is usually shown as 2Fe2O3 plus 3Ca4Fe plus 3CO2. Metal oxides can be reduced by organic compounds. This redox process is the basis for many important transformations in chemistry, such as the detoxification of drugs by the P450 enzymes and the production of ethylene oxide, which is converted to antifreeze. In such systems the metal center transfers an oxide ligand to the organic compound followed by regeneration of the metal oxide, often by oxygen in air. Hydrolysis. Oxides of more electropositive elements tend to be basic. They are called basic anhydrides. Exposed to water, they may form basic hydroxides. For example, sodium oxide is basic A-. When hydrated, it forms sodium hydroxide. Oxides of more electronegative elements tend to be acidic. They are called acid anhydrides. Adding water, they form oxosides. For example, dichlorine heptoxide is acid. Perchloric acid is a more hydrated form. Some oxides can act as both acid and base. They are amphoteric. An example is aluminium oxide. Some oxides do not show behavior as either acid or base. The oxide ion has the formula O2A. It is the conjugate base of the hydroxide ion, OA, and is encountered in ionic solids such as calcium oxide. O2A is unstable in aqueous solution, or its affinity for H+ is so great that it abstracts a proton from a solvent H2O molecule, O2A plus H2OA2OA. The equilibrium constant of aforesaid reactions is pK 22. In the 18th century, oxides were named kales or kaleses after the calcination process used to produce oxides. Cal was later replaced by oxide. Nomenclature and formulas. Sometimes, metal-oxygen ratios are used to name oxides. Thus, NBO would be called niobium monoxide and TO2 as titanium dioxide. This naming follows the Greek numerical prefixes. In the older literature and continuing in industry, oxides are named by contracting the element name with A. Hence alumina, magnesia, chromia, R, respectively, Al2O3, MgO, Cr2O3. Special types of oxides are peroxide, O22A, and superoxide, O2A. In such species, oxygen is assigned higher oxidation states than oxide. The chemical formulas of the oxides of the chemical elements in their highest oxidation state are predictable and are derived from the number of valence electrons for that element. Even the chemical formula of O4, tetraoxygen, is predictable as a group 16 element. One exception is copper, for which the highest oxidation state oxide is copper, 2, oxide and not copper, I, oxide. Another exception is fluoride, which does not exist as one might expect as F2O7 but as OF2. Since fluorine is more electronegative than oxygen, oxygen difluoride does not represent an oxide of fluorine, but instead represents a fluoride of oxygen. Examples of oxides. The following table gives examples of commonly encountered oxides. Only a few representatives are given, as the number of polyatomic ions encountered in practice is very large. See also, other oxygen ions: ozonide, O3A, superoxide, O2A, peroxide, O22A and dioxygenyl, O2+. Suboxide, oxaholide, oxyanion. See category, oxides for a list of oxides. Salt. References